Welcome to today's problem walkthrough. We'll be tackling LeetCode problem number 475, heaters. This is a fascinating problem that challenges us to optimize the placement of heaters so they can provide warmth to every house in a given area. Let's dive in and explore the problem statement, its constraints, and the best approaches to solve it. The problem centers around heating houses during the winter. Imagine you have a row of houses and a set of heaters placed at specific positions on a one-dimensional grid. Each heater has a fixed heating radius, meaning it can warm houses within a certain range, from its position minus the radius to its position plus the radius, inclusive. The challenge is to determine the smallest possible radius that ensures every house is within the range of at least one heater. You'll receive two inputs, a list of integers representing the positions of the houses and another list for the positions of the heaters. For example, if the houses are at positions 1, 2, and 3, and there's a heater at position 2, your goal is to calculate the minimum radius needed to cover all the houses. Ultimately, the task is to return this minimum radius as the output. The output of the problem is a single integer, which represents the minimum radius needed to ensure that all houses are covered. To understand this better, consider an example where the houses are at positions 1, 2, and 3, and there's a single heater at position 2. In this case, a radius of 1 is sufficient. Why? Because the heater at position 2 can cover positions 1, 2, and 3 with this radius, which includes all the houses. Therefore, the output for this input would be 1. The key is to find the smallest radius that guarantees no house is left out of the heating range. Now, let's look at another example where the houses are at positions 1 and 5, and there's only one heater at position 2. In this scenario, a radius of 3 is needed. With this radius, the heater at position 2 can cover from position -1 to position 5. This range ensures both houses at positions 1 and 5 are covered. Since no smaller radius would work, the minimum radius required in this case is 3. Here's one more example to illustrate how multiple heaters can work together. Suppose the houses are at positions 1, 2, 3, and 4, and there are heaters at positions 1 and 4. With a radius of 1 for each heater, the heater at position 1 can cover houses at positions 1 and 2, while the heater at position 4 can cover houses at positions 3 and 4. This ensures all houses are covered, and because no smaller radius would suffice, the output is 1. This example highlights how the placement of multiple heaters can reduce the required radius. Finally, let's go over the constraints and some edge cases. The constraints specify that the number of houses and heaters can go up to 10,000, and their positions can be as large as 1 billion. Each position is unique, so you won't have overlapping houses or heaters. As for edge cases, consider a single house at position 1 and a heater far away at position 10. Here, the radius must be large enough to bridge that gap. Another scenario is when there are multiple houses but just one heater, where the radius must cover the farthest house. Lastly, if heaters are placed exactly at the positions of houses, the required radius could be 0 because each house is already directly heated. These cases demonstrate the variety of situations your solution needs to handle efficiently. To tackle the heaters problem, the first and most straightforward approach we can consider is brute force. The intuition here is simple. For each house, we calculate the distance to every heater and identify the nearest one. Once we find the minimum distance for that house, we record it. The goal is to determine the maximum of these minimum distances across all houses, as this represents the smallest heater radius needed to cover every house. However, this approach comes with trade-offs. It has a time complexity of n*m, where n is the number of houses and m is the number of heaters, because we're performing a comparison for every house heater pair. While it's easy to implement, this method becomes highly inefficient when the number of houses or heaters grows significantly. Additionally, it uses constant space, but the computational overhead makes it impractical for larger inputs. This inefficiency prompts us to explore more optimized solutions. To address the inefficiency of the brute force approach, we can optimize by incorporating sorting and binary search. By sorting both the houses and heaters arrays, we can use binary search to efficiently find the closest heater for each house. Specifically, for every house, we locate the positions of the nearest heaters using binary search, calculate the distances to these heaters, and take the smaller of these distances. The maximum of these distances across all houses gives us the required heater radius. Sorting the heaters allows us to reduce the complexity of finding the nearest heater to O log m, and as a result, the overall time complexity becomes O n log m plus m log m. The first term accounts for binary search being performed for each house, and the second term comes from sorting the heaters. This approach is both efficient and straightforward, relying on the sorted order to minimize unnecessary comparisons. However, it assumes that sorting is feasible within the given constraints, and while efficient, it still has some computational overhead due to repeated binary searches. An alternative way to optimize the solution is by using the two-pointer technique. After sorting both the houses and heaters arrays, we use two pointers to traverse the arrays. For each house, we adjust the heater pointer to ensure we consider the closest heater. Once the pointer is positioned correctly, we calculate the distance between the house and the nearest heater. This distance is then tracked to find the maximum value across all houses, which determines the required heater radius. The two-pointer approach eliminates the need for binary search, making it more straightforward while still leveraging the efficiency of sorted arrays. The time complexity is O n log n plus m log m, where the sorting step dominates, and the space complexity remains constant. This method simplifies implementation while maintaining efficiency, offering a good balance between speed and clarity. It ensures that we avoid redundant computations, making it an attractive choice for solving the problem. After evaluating several approaches, the two-pointer method stands out as the chosen strategy for solving the heaters problem. Its efficiency, with a time complexity of O n log n plus m log m, avoids the nested loops of the brute force approach while being simpler to implement than the binary search-based method. By sorting the arrays, we ensure that the closest heater is always considered for each house, which minimizes unnecessary computations. This method directly aligns with our goal of reducing computational overhead without compromising correctness. Key insights from this approach include the importance of sorting for efficient comparisons and the realization that the maximum of the minimum distances determines the required radius. The simplicity, combined with efficiency, makes the two-pointer technique an ideal choice for this problem. When comparing the two-pointer approach to binary search, both methods are efficient, but the two-pointer technique stands out due to its simplicity and lack of additional overhead. In contrast to the brute force approach, the two-pointer method drastically reduces computation time, making it well-suited for larger inputs. This comprehensive evaluation highlights how the chosen strategy balances efficiency and ease of implementation. By leveraging sorting and focusing on minimizing unnecessary computations, the two-pointer approach emerges as the most practical and effective solution for the heaters problem. In this problem, we are tasked with determining the minimum radius of heaters required to ensure that every house is within the range of at least one heater. A house is considered covered if it falls within the heater's radius. To solve this efficiently, we start by parsing the input, two lists representing the positions of houses and heaters. These lists are then sorted in ascending order. Sorting is crucial because it allows us to use techniques like binary search or two pointers to find the closest heater for each house more efficiently. We also initialize a variable called min_radius, which will store the maximum of all minimum distances calculated between houses and their nearest heaters. Additionally, we set up two pointers, one for traversing the sorted list of houses and another for the sorted list of heaters. These pointers will help us systematically evaluate the distances between houses and heaters as we proceed through the algorithm. The next step involves iterating through each house to find its nearest heater. To do this, we use the two-pointer technique. Here, one pointer keeps track of the current heater, while the other moves through the list of houses. For each house, we compare its distance to the current heater with its distance to the next heater, if one exists. By adjusting the pointer for the heaters, we can ensure we always identify the closest heater for the current house. Once the nearest heater is found, we calculate the distance between the house and this heater. This distance represents the minimum radius required to cover that house. To determine the overall minimum radius for all houses, we update min_radius to be the maximum of its current value and the distance we just calculated. After processing all houses, min_radius will hold the smallest possible radius needed to ensure every house is covered. The key challenge in this problem lies in efficiently finding the nearest heater for each house. A naive approach, where we compare every house to every heater, results in a time complexity of O(n*(m), which is impractical for large inputs. However, by sorting the houses and heaters lists, we can leverage their relative positions to reduce the complexity. Sorting enables us to use either binary search or the two-pointer technique to quickly locate the nearest heater. If the heaters are fixed and queried multiple times, binary search is optimal because it allows us to find the closest heater in logarithmic time. However, for a one-pass solution, the two-pointer approach is simpler and faster. The sorted arrays and two-pointers work together to minimize redundant comparisons, making the algorithm more efficient overall. Now let's analyze the complexity of the algorithm. The time complexity consists of two main components, sorting and traversal. Sorting the houses and heaters lists takes O(n log n plus m log m, where n is the number of houses and m is the number of heaters. The subsequent two-pointer traversal operates in O(n plus m, as each element in both lists is processed at most once. This gives the overall time complexity of O(n log n plus m log m. Space complexity is O(1), since we perform all operations in place without using additional data structures. When considering edge cases, the algorithm handles scenarios such as having only one house or one heater by calculating the absolute distance. If a house and heater occupy the same position, the required radius is 0. Even if some houses fall outside the range of all heaters, the algorithm accurately calculates the distance to the nearest heater, ensuring robust handling of various inputs. To illustrate the algorithm, let's walk through an example. Suppose we have houses equals 1, 5, 10, and heaters equals 2, 8. First, we sort both lists, resulting in houses equals 1, 5, 10, and heaters equals 2, 8. Next, for each house, we identify the closest heater. For house 1, the nearest heater is at position 2, with a distance of 1. For house 5, the closest heater is at position 8, yielding a distance of 3. Finally, for house 10, the nearest heater is also at position 8, with a distance of 2. The maximum distance across all houses is 3, so the minimum radius required to cover all houses is 3. By systematically following these steps, the algorithm ensures that every house is covered with the smallest possible heater radius. This solution efficiently calculates the minimum radius of heaters required to ensure all houses are covered. Here's how the code works. 1. Sorting. Both the houses and heaters lists are sorted at the outset. This pre-processing step simplifies the logic of comparing distances between houses and heaters, ensuring the algorithm works in a linear pass. 2. Initialization. The radius variable is initialized to 0. This variable will store the maximum distance any house is from its closest heater, which ultimately determines the minimum heater radius required. 3. Pointer setup. A pointer j is used to keep track of the current heater being considered. This allows us to efficiently find the closest heater for each house. For iterating through houses, for each house, the algorithm adjusts the pointer j to ensure the closest heater is considered. The condition in the while loop ensures that the pointer moves to the next heater only if it is closer to the current house than the previous heater. 5. Distance calculation. Once the closest heater for a house is determined, the absolute distance between the house and the heater is calculated. 6. Radius update. The radius is updated to the maximum of its current value and the distance for the current house. This ensures that the radius always accounts for the farthest house from its closest heater. 7. Result. After all houses are processed, the radius variable contains the minimum heater radius required to cover all houses, which is returned as the result. This approach is efficient with a time complexity of O(n log n plus m log m, where n and m are the lengths of the houses and heaters lists, respectively, due to the initial sorting step. The subsequent iteration through houses and heaters is linear, making this solution well suited for large inputs. Here, we start by importing the necessary Java utilities and defining our solution class along with the findRadius method. The first step in solving this problem is to sort both the houses and heaters arrays. Sorting helps simplify the task of finding the nearest heater for each house. Next, we initialize the variable radius to track the maximum minimum distance required, and heater index to keep track of the current heater we are considering. Now, we iterate through each house in the sorted houses array. For each house, We determine the closest heater by comparing the distances to the current heater and the next heater in the sorted heaters array. If the next heater is closer to the house, we increment heater index to move to it. This ensures that for each house, we are always calculating the distance to the nearest heater available at that point. Once the nearest heater is identified, we calculate the distance between the house and the heater. Then, we update the radius to be the maximum distance encountered so far, as this ensures that all houses are within the required distance of at least one heater. Finally, after iterating through all the houses, the method returns the calculated radius. This value represents the minimum radius needed to ensure that every house is within range of at least one heater. The logic ensures that we account for all edge cases, such as houses located between two heaters or at the ends of the array, by continuously updating the radius to accommodate the farthest house. This implementation leverages sorting and a single pass through the houses, making it efficient and well suited for the problem constraints. The solution is now complete and ready to handle any valid input arrays for houses and heaters. In this example, we start with the input houses equals 1, 2, 3, and heaters equals 2. The first step is to sort both arrays, although in this case, they are already sorted. We then initialize two variables, radius, which keeps track of the maximum distance between any house and its nearest heater, and j, a pointer to navigate through the heaters array. For the first house, which is located at position 1, we check the closest heater. Since the pointer j is at 0, the closest heater is heaters, 0 equals 2. The distance between the house and the heater is calculated as abs, 2 to 1 equals 1. We then update the radius to be the maximum of its current value, 0, and this distance, so radius becomes 1. For the second house, located at position 2, the heater pointer j still points to the same heater, heaters, 0 equals 2, as it's the closest. The distance between the house and the heater is abs, 2 to 2 equals 0. We update the radius to be the maximum of its current value, 1, and this distance, which means radius remains 1. Next, we process the third house at position 3. The heater pointer j again points to heaters, 0 equals 2, which is the nearest heater. The distance is calculated as abs, 2 to 3, equals 1, and updating radius with the maximum of 1 in this distance results in radius staying at 1. Finally, we find that the minimum radius required to heat all houses in this scenario is 1. Now we move to a slightly more complex example with houses equals 1, 4, 6, and heaters equals 2, 5. As always, we start by sorting the arrays, which are already in order. We initialize radius to 0 and the heater pointer j to 0. For the first house, located at position 1, the closest heater is heaters, 0 equals 2. The distance between the house and the heater is abs, 2 to 1 equals 1. We update radius to be the maximum of its current value, 0, and this distance, resulting in radius equals 1. For the second house at position 4, the heater pointer initially points to heaters, 0 equals 2. However, since the heater at heaters, 1 equals 5 is closer to house 4, we move the pointer j to 1. The distance to this closer heater is abs, 5 to 4 equals 1. We update radius to be the maximum of its current value, 1, and this distance, so radius remains 1. For the third house at position 6, the heater pointer j stays at 1, pointing to heaters, 1 equals 5, which is the nearest heater. The distance between the house and the heater is abs, 5 to 6 equals 1. Updating radius with the maximum of its current value, 1, and this distance keeps radius at 1. Thus, the minimum radius required to heat all houses in this example is 1. In this example, we have houses equals 1, 5, 10, and heaters equals 2, 8. After sorting the arrays, we initialize radius to 0 and the heater pointer j to 0. Starting with the first house at position 1, the closest heater is heaters, 0 equals 2. The distance between the house and the heater is abs, 2 to 1 equals 1. We update radius to the maximum of its current value, 0, and this distance, resulting in radius equals 1. Next, for the house at position 5, the heater pointer initially points to heaters, 0 equals 2. However, the heater at heaters, 1 equals 8 is closer to house 5, so we move the pointer j to 1. The distance to this closer heater is abs, 8 to 5 equals 3. Updating radius with the maximum of its current value, 1, and this distance gives radius equals 3. For the final house at position 10, the heater pointer J remains at 1, pointing to heaters, 1 equals 8, which is the nearest heater. The distance between the house and the heater is abs, 8 to 10, equals 2. Updating radius with the maximum of its current value, 3, and this distance keeps radius at 3. Therefore, the minimum radius required to heat all houses in this case is 3. To analyze the time complexity of our solution, we start with the sorting step. Both the houses and heaters arrays need to be sorted before we begin the main logic. Sorting the houses array takes O, n log n, where n is the number of houses, and sorting the heaters array takes O, m log m, where m is the number of heaters. Together, the sorting contributes O, n log n plus m log m, to the overall complexity. Next, as we iterate through each house in the houses array, the main loop runs O, n, times, once for each house. Within this loop, we adjust the pointer J to find the closest heater to the current house. The pointer only moves forward, which means that over the entire iteration, the total movements of J across all houses are at most m, the number of heaters. This step has a combined complexity of O, n plus m, for the entire process. Now, calculating the maximum radius for each house is straightforward. For each house, we compute the distance to the closest heater and update the maximum radius if needed. Since these are constant time operations for each house, this step contributes O, n, in total. When we combine all these elements, the dominant terms are sorting, which is O, n log n plus m log m, and the main iteration, which is O, n plus m. Therefore, the overall time complexity of the solution is O, n log n plus m log m. Shifting to space complexity, the primary contributors are the input arrays, houses and heaters, which require O, n plus m, space. Sorting is performed in place using timsort, the default sorting algorithm in Python, so no additional space is required beyond the input arrays. Additionally, the algorithm uses a few auxiliary variables such as radius, J, and distance, all of which require constant space. This means the extra space used is O1. Combining all factors, the overall space complexity is dominated by the input storage, resulting in O, n plus m. To put this into perspective, let's compare this solution with a brute force approach. In a naive method, we would calculate the distance from each house to every heater and determine the closest heater for each house. This approach involves two nested loops, one iterating over all houses, O, n, and the other over all heaters, O, m. The total time complexity for this brute force approach would be O, n asterisk m, which becomes infeasible as the number of houses or heaters grows larger. Clearly, the optimized solution is far superior. The optimized approach achieves its efficiency through sorting and the use of a monotonic pointer. Sorting ensures the input arrays are processed in a structured manner, while the pointer eliminates redundant comparisons, leading to an overall time complexity of O, n log n plus m log m. When analyzing specific cases, the best case scenario involves minimal pointer movements during the iteration, but the time complexity remains dominated by the sorting step at O, n log n plus m log m. For the average and worst cases, the algorithm still performs efficiently, as the pointer guarantees no more than O, n plus m, operations, even in the most challenging configurations. This efficiency is mathematically supported by the fact that the linear iteration after sorting is bounded by O, n plus m, making the sorting step the driving factor. Therefore, the time complexity consistently remains O, n log n plus m log m, a significant improvement over the brute force alternative. When solving this problem, there are several common mistakes to watch out for. First, ensure that you sort the heaters array before using binary search. This is critical because binary search operates under the assumption that the array is sorted. If it's not, the search will yield incorrect results. Next, it's important not to confuse the position of the heater with its coverage. The heater's position alone doesn't determine its effect, you must calculate the absolute distance between the heater and the house being considered. Another common pitfall is neglecting to handle edge cases properly. For example, what happens if all houses fall outside the range of every heater? Or if there are multiple heaters at the same position? You also need to account for scenarios with only one heater or one house in the input. Finally, avoid inefficient computations for large inputs. Using nested loops to calculate distances between every house heater pair can quickly lead to timeouts, especially when the input size grows large. Instead, aim for optimized approaches like sorting, binary search, or two-pointer techniques to handle these scenarios efficiently. Off-by-one errors are another frequent issue, especially when implementing binary search or two-pointer techniques. Miscalculating bounds or failing to update pointers correctly can lead to subtle bugs, so it's important to validate your implementation with test cases that cover edge scenarios. From an interview perspective, this problem showcases how well you can identify patterns and optimize solutions. Binary search and two-pointer techniques are key here, as they allow you to improve upon brute force methods. Interviewers often use this problem to evaluate how you handle repetitive computations and whether you can optimize them effectively. Additionally, demonstrating how your solution addresses edge cases like no heaters, multiple heaters at the same position, or houses outside the heater range is essential. Be prepared to discuss the time complexity of different approaches, such as O(n*(m) for brute force versus O(n)log(m) for binary search, and explain why your chosen solution is optimal for the constraints. Above all, focus on clearly communicating the intuition behind your approach. For example, explain how binary search efficiently identifies the nearest heater rather than diving straight into the code. This problem is closely connected to other LeetCode problems that use similar techniques. For instance, LeetCode 875, Cocoa Eating Bananas, deals with binary search to find the smallest possible value. LeetCode 162, Find Peak Element, also involves binary search but emphasizes handling edge cases. LeetCode 1482, Minimum Number of Days to Make M Bouquets, applies optimization via binary search, while LeetCode 410, Split Array Largest Sum, uses binary search on the result. It's worth exploring these problems to strengthen your understanding of how binary search can be adapted to different contexts. When considering alternative approaches to the heaters problem, the brute force method involves calculating the distance between each house and every heater and determining the minimum radius required. While this is straightforward to implement, it becomes computationally expensive for large inputs, with a time complexity of O(n*(m). On the other hand, the binary search approach involves sorting the heaters array and efficiently finding the closest heater for each house. This significantly reduces the computational cost to O(n)log(m), though it does require careful handling of edge cases and the additional overhead of sorting. Another efficient alternative is the two-pointer technique, which involves traversing the sorted houses and heaters arrays simultaneously. This approach dynamically minimizes the distance between houses and heaters, achieving a time complexity of O(n+m). While faster than binary search, it may be less intuitive and demands a solid grasp of pointer movement logic. Finally, there's the greedy algorithm, where you aim to place heaters optimally to minimize the maximum distance to any house. While this strategy can be effective for certain variations of the problem, it may not work universally and can be more challenging to implement correctly. Each of these approaches has its own trade-offs, so it's important to choose the most appropriate one based on the problem's constraints and requirements. Great job! We've covered the problem, explored solutions, and discussed the trade-offs. Remember, the key is to analyze constraints and optimize for performance where needed. Keep practicing, and don't hesitate to revisit this problem for deeper understanding. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!